Hello friends, in this video let us discuss combinational basics and sequential basics of digital system design using Verilog. Here I am referring Peter J. Ashenden book. So in this combinational circuits we will be talking about Boolean function and Boolean algebra. Also we are going to discuss about binary coding and we are going to discuss about combinational components and circuits, verification of combinational circuits. In the case of sequential circuits, we are going to talk about storage element. The storage elements, the basic storage element means a flip-flop. Group of flip-flops is called as register. In order to store the data at the time you are in need of shift registers. Also, if you want to perform the operation something like multiply by 2 or divide by 2, you can perform left shift or right shift. Next is you will be talking about the basic difference between a latch and a flip-flop. Also you're going to talk about counters. You are having two variants of counter. The first one is synchronous counter and the second one is asynchronous counter. In the digital circuits we will be talking about ring counter and twisted counter also. You're going to talk about sequential data path and control. In the case of finite state machine you're going to talk about Mealy model and Murray model. You're going to talk about clocked synchronous timing methodology. In the case of clocked synchronous timing methodology, you're going to talk about asynchronous inputs, verification of sequential circuits, also synchronous timing methodologies. All these things you're going to discuss in this video. Let us discuss combinational basics in detail. So first thing is we need to talk about Boolean algebra and Boolean functions. So what do you mean by a Boolean function? Say suppose you want to rig up with some expression. At the time you are in need of AND gate, you are in need of OR gate, you are in need of NOT gate. So this is referred as basic gates. Able to follow? So this AND gate is going to perform logical AND operation, OR gate is going to perform logical OR operation, NOT gate is going to perform negation operation. Now let us learn the truth table for AND gate, OR gate and NOT gate. Let me assume my inputs are x and y, output z equals to, for an OR gate, output z equals to x plus y, nothing but x OR with y. If I am considering AND gate, the expression for AND gate z equals to x AND with y. If I am considering a NOT gate, then if my input is x, then output z equals to x bar. So I am considering two input OR gate and two input AND gate. So if I am having two inputs, the number of combinations will be 2 power 2, which is equals to 4. So the combinations are, I am considering a binary code, so it is 0001 1011. For a case of OR gate, x OR with y, nothing but for 0 0 I will be getting output as 0, rest of the cases I will be getting output as 1. Similarly for the AND gate, if all my inputs are 1, then only my output is 1, rest of the cases it is 0. But in the case of NOT gate, if I am giving logic 0, I will be getting logic 1. If I am giving logic 1, I will be getting logic 0. Nothing but your output is negation of your input or complement of your input. Next, let us consider one example. What they are given is f equals to x plus y into z bar. So you are having logical OR operation and logical AND operation you have to negate, nothing but x OR with y, so you are in need of OR gate. So the intermediate output here will be x OR with y. Able to follow? And z is the input for the NOT gate, so the intermediate output will be z bar. So these two things I am going to add, so I will be getting x plus y into z bar. Able to follow? Next, let us learn the truth table for x plus y into z bar. So I am having 3 inputs, so the number of combinations equals to 2 power 3, which is equals to 8 combinations ranging from 0 0 0 to 1 1 1. X plus y, nothing but 0 plus 0 into z bar. Z bar is 1, nothing but 0 I will be getting. 0 1 let me consider, 0 1 0 let me consider, 0 1. So or if I am performing I will be getting 1 and with a 0 bar, nothing but I will be getting 1. So this is how you are going to rig up the truth table for the given expression. So how you are going to write a Verilog code for the given expression. So the given expression is x plus y into z bar they have given. Let me assign this to a. That means a equals to x plus y into z bar. So how I am going to write the Verilog code means starting with module followed by module name. Let me consider example 1. Then my inputs are X, Y, Z and my output is A. Able to follow? Next, I am going to explicitly write input. Which and all are my inputs? Inputs are X, Y, Z and the dependent variable, that is my output. So output, only one output I am having, that is A. So I am going to make use of data flow modeling. I will be writing assign A equals to X OR with Y and with negation Z. Able to follow? At last I have to terminate the program by writing end module. End module is a single word. Able to follow? This is how to write a piece of Verilog code for the given expression, that is X plus Y into Z bar. Next, you have to remember the symbol, also the truth table for NOR gate, NAND gate, XOR gate, XNOR gate. Also you are going to represent with the help of AND or invert or and invert, especially if you want to talk about the cost of the circuit. Next, what is NOR gate? NOR gate is nothing but OR gate followed by a NOT gate, or it is bubbled AND gate. Similarly, NAND gate is AND gate followed by a NOT gate. One more way is it is bubbled OR gate. Able to follow? Next, XOR gate is used for inequality detector, XNOR gate is used for equality detector. These things also you have to remember. Also, we know that NAND gate and NOR gate is called as universal gate. Apart from NAND gate and NOR gate, you will be having multiplexers and demultiplexers is also considered to be universal gate. Also, encoders and decoders is also considered as a universal gate. Apart from this, ACE gate is also an universal gate. Let us learn the truth table for NOR gate, NAND gate, XOR gate and XNOR gate. I am having two inputs, nothing but the number of combinations is 4. The combinations are 0, 0, 0, 1, 1, 0, 1, 1. In the case of NOR gate, which is complement of OR gate, so I am getting the truth table as 1 followed by 3 zeros. But if I am considering NAND gate, it is the complement of AND gate, nothing but 1, 1, 1, 0. XOR gate, it is nothing but whenever my inputs are different, then only I will be getting output as 1, nothing but for 0, 0 and 1, 1, I will be getting zeros only. XOR gate complement is XNOR gate, nothing but XNOR gate is used for equality detector, nothing but for 0, 0 combination and 1, 1 combination I will be getting 1, rest of the cases I will be getting 0. This is the truth table for NOR gate, NAND gate, XOR gate and XNOR gate. You should know the clock division circuitry using buffer tree. Now look at over here, in the case of synchronous design, each and every clock pulse should be reached for each and every flip-flop at a specific time, nothing but at the given time only the clock should arrive. If there is a delay in the clock arrival, then it results in clock skew. So in order to overcome this clock skew, you are going to make use of buffers. Let us learn Boolean algebra. The first law is commutative law. What it says is commutative law for addition. X plus y equals to y plus x, nothing but 2 plus 3 which is equals to 3 plus 2. Commutative law for multiplication, what it says is x into y which is equals to y times of x, nothing but 2 into 3 which is equals to 3 into 2. But the same thing, commutative law is not applicable for subtraction as well as for division. Say suppose if I am writing 2 minus 3 which is not equals to 3 minus 2. Or the other way is 2 divided by 3 is not equals to 3 divided by 2. So commutative law is applicable only for addition as well as multiplication. But it is not applicable for subtraction as well as for division. Able to follow? Similarly, associative law for addition, what it says is x plus y of z which is equals to x plus of y plus z. The other expression is associative law for multiplication. What it says is x into y of z which is equals to x into of y times of z. Similarly, the distributive law, what it says is x times of y plus z, which is equals to x plus y times of x plus z. Commutative law for addition, x plus y times of z, which is equals to x plus y times of x plus z. Similarly, identity law you should know, x plus 0, which is equals to x, x into 1 equals to x. Say suppose x equals to 0, then I will be getting 0 plus 0 is 0. Say suppose x equals to 1, then 1 plus 0 is 1. Complement law, x plus x bar equals to 1, x into x bar, which is equals to 0. Say suppose if x equals to 0, then 0 into 1 is 0. 0 plus 1 is 1. So this is what you mean by complement law. The first one is idempotence law. What it says is x plus x, which is equals to x, or x into x, which is equals to x, nothing but 1 plus 1 is not equals to 2, nothing but 1 0, it is 1 only. Or in the case of multiplication, 1 into 1 is 1 only. Further identity law, what it says is x plus 1, which is equals to 1. Irrespective of the value of x, nothing but 0 plus 1 is 1 only, 1 plus 1 is also 1 only. Next is x into 0 is 0. Irrespective of the value of x, my output remains 0. Next law is absorption law, x plus xy, which is equals to x. How it will be coming is x times of 1 plus y, which is equals to x times of, what is 1 plus y? It is 1. So I'll be getting x, right? So next is De Morgan's law. De Morgan's law is very important. What it says is x plus y the whole bar, which is equals to x bar into y bar. This is one law. One more law is x into y the whole bar, which is equals to x bar plus y bar. These are the two laws for De Morgan's law. De Morgan's law is very important. Please go through it. These things you have to remember. This is the symbol for AND gate, OR gate, NAND gate, NOR gate, XOR gate, XNOR gate, NOT gate. So equivalent expression also they have given. Please go through it. Next, you have to write the truth table for y equals to a into b bar plus c bar. So you will be having 3 inputs. So number of combinations equals to 2 power 3, which is equals to 8, starting from 0 0 0 to 1 1 1. Also you have to write the truth table for the Boolean expression a dot b the whole bar, which is equals to a bar plus b bar, which is they are asking us to prove the De Morgan's law. So let me consider my inputs are a and b, then my outputs are a into b the whole bar. This is one expression, and one more expression is a bar plus b bar. Since I am having 2 inputs, the number of combinations are 4, nothing but 0 0 0 1 1 0 1 1. 0 into 0, nothing but 0, 0 complement is 1. 0 and with 1 is 0, complement is 1. 1 and with 0 is 1, sorry, 1 and with 0 is 0, complement is 1. 1 and with 1 is 1, complement is 0. Next, a bar plus b bar. 0 bar is 1, rest of the things don't care. 0 bar is 1. 0 bar, 1 bar, nothing but 0, plus 0 bar is 1. This is 0. So these two cases I am getting the same. Hence I can prove the De Morgan's law, that is a dot b the whole bar, which is equals to a bar plus b bar. What do you mean by a Boolean expression? That is sum of product form. Say if I am writing ab plus bc, then it is sum of product. But if I am writing a plus b of b plus c, it is product of sum. These two things are very important. In digital electronics, especially in K-map solving, you will be encountering sum of product as well as product of sum. Write the truth table for AND or invert. So I have shown in figure 2.3. You should be in a position to write. Why are buffers used in digital circuits? Buffers are used to store the information. So the microprocessor has to interact with the lower peripheral device. At that time, it is going to make use of buffers. Use of don't care. Don't care means you can consider don't care the values. So don't care, I can tell, that is represented as x. X can take 0 or it can take 1 also. So don't cares are used for simplification of logical expression, also to reduce the cost of the circuit. Write the dual of the Boolean expression they have given. So what they have given is a plus b times of c the whole bar, which is equal to a bar into b bar plus a bar into c bar. What do you mean by dual? Dual in the case you will be having two steps. The logical OR should be converted into logical and vice versa. Logic 0 should be converted into logic 1 and vice versa. This is how you are going to take a dual of a function. For detailed explanation, I'll be putting a link in the description. Please go through the video. Next, if I want to take the dual of the function, then write the expression as it is a, b, c. Wherever you are having logical OR, replace by logical and make sure the priority should be given for logical and then you have to give the priority for logical OR. Able to follow? Which is equals to wherever you are having and replace by OR. So you'll be getting a bar plus b bar into a bar plus c bar. So you have to give the priority for AND gate followed by OR gate. So in the case of duality of a function, you have to replace logical OR with logical and logic 0 with logic 1. This is how you are going to perform dual of a function. If you want to take complement of a function, what you have to do is, first step is you have to take the dual of a function. Next step is you have to complement each literals. Nothing but if you are having a, write a bar. If you are having b, write b bar. If you are having c bar, you should write it as c. Write a Verilog assignment statement to model the Boolean equation f equals to a dot b bar plus c bar. How you are going to write in a data flow modeling means assign f equals to a and with negation b or with negation c. This is how we are going to write a piece of Verilog code. Before do that, you have to write module name. You have to explicitly define which is input and which is output. At last you are going to write the program. At last you have to exit the program by writing end module. Why should we generally not to try to optimize Boolean equations manually when modeling them in Verilog? Because of errors, because of human errors. And main thing is optimization is a major hurdle. Optimization is a major hurdle. Next, let us talk about binary coding. So in the case of binary coding, we are going to make use of 8421 code. Say suppose you are having 10 variants of your input. So how I am going to encode means this starting value I am going to write it as 00 and ending value is 1010. If you are having up to 15, you are going to write 1111. So this is how you are going to perform an encoding. Right? How it came means you are going to make use of 8421 code. Now look at over here, you are having a traffic light signals. The first one is red, yellow, green. If you want to represent red as 000 or 001, let me assume. Yellow you are going to represent as 010. Green you are representing as 100. Nothing but you are in need of 3 bits. What if I am representing red as 00, yellow as 01, green as 10? Nothing but I have saved 1 bit. So this is what do you mean by binary coding. Nothing but you are going to assign some code words. Similar example, let me take, you will be having an inkjet printer which is going to have some color code: black, cyan, magenta, yellow, light and cyan as well as light magenta. If I am encoding black as 000, cyan if I am encoding as 001, magenta I am encoding it as 010, yellow I am encoding it as 011, light cyan I am going to encode it as 100, light magenta I am going to encode it as 101. Rest of the 2 things also I can encode. So 6 colors are there, but I am not making use of 6 bits. I am going to make use of only 3 bits. The other way to represent is log of n. N is number of cases. Say it is log 6 to the base 2. So I will be getting 3. Nothing but 3 bits are required in order to encode. All the intermediate results you are going to write it as wire, but all the outputs, if you want to store for further processing point of view, we are going to declare it as registers. This is very, very important. Now, at the communication point of view, if you are transmitting the data, always noise is a major hurdle. So the bits are going to flip. So at that time, the one simple mechanism is you can make use of parity check. But if multiple bits are going a flip, then parity check is not a useful one. Nothing but parity check is not the optimization technique. You need to talk about what do you mean by even parity and what do you mean by odd parity. In the case of even parity, one parity bit you have to assign that depends on number of ones in the elements. So if there are odd number of ones, so in order to make it even, you are going to add one. Say suppose if I am talking about odd parity, if I am having even number of ones, then to make it odd, I am in need of 1. Or I am going to assign parity bit as 1. Rest of the cases it is 0. Technical quiz questions are very, very important. How many code words are possible with a code of 5 bits? So if you are having a code of 5 bits, then the number of combinations varies from 00000 to 11111. Nothing but it is varying from 0 to 31. Total number of combinations is 32. What is the minimum number of bits needed to encode information with the 12 possible values? Say 12 possible values are there. So how many bits are required is you are in need of 4 bits. You are in need of 4 bits. 4 bits are enough in order to encode 12 possible values. 12 possible values means let me consider 1011. This is 12 combinations. So in order to encode the 12 combinations, I am in require of only 4 bits. So one more question they have given, devise a hot code to represent the days of the week Monday to Sunday. So there are totally 7 days. Monday I am going to encode it as 000. Tuesday I am going to encode it as 001. Wednesday I am going to encode it as 010. Thursday I am going to encode it as 011. Friday I am going to encode it as 100. Saturday I am going to encode it as 101. Sunday I am going to encode it as 110. So I am in need of 3 bits. So if I am having 3 variables, then the number of combinations equals to 8 combinations I can represent. Write a Verilog declaration for net name W representing the 8-bit binary code. Write a Verilog assignment that drives each bit of W with a 0 level. So all these things are very, very important. Please go through it. Combinational components and circuits are very, very important. The first topic is encoders and decoders. Encoders and decoders is used in communication. Encoders are used in order to encode the data, nothing but in order to reduce the data streams, or for security point of view, we are going for encoders and decoders. So the encoders representation is 2 power n cross n, and the decoder representation is n cross 2 power n. So one example of encoder is priority encoder. This will be used in sharing of printers, sharing of any hardware peripherals. At that time you are going to make use of priority encoders. Priority encoders means you are going to set the priority. Nothing but in a company you are going to assign the highest priority to a director, followed by a manager, followed by worker. Next, let us talk about BCD code and 7-segment decoders. So in the case of BCD, nothing but binary coded decimal, it is nothing but decimal representation, that is 00002 1001. Nothing but total number of representation is up to 10 you can represent. So the data is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, followed by it is 10, 11, 12, 13, so on to 19, followed by 20. Like that you are going to represent. The 7-segment decoder means it is used in a display. You will be having 2 variants of display. The first one is LED display and the second one is LCD display. This LED display you are going to use in the case of traffic signals where intensity is more. So this LCD display you will be using in wristwatches where intensity is not a major hurdle. And LED display you are going to use in indication. Example, whether the TV is on or off, you are going to indicate via LED. Also, the AC is turned on or turned off, you are going to indicate with the LED. So this LED is used as an indicators. Able to follow? Next, let us talk about 7-segment decoder. Now, if I want to display some message, I want LED display or LCD display. What if I am using LED display is the big question. So we'll be having 7 LEDs over here: A LED, B, C, D, E, F, G. Say suppose if I want to display numbers or characters. If I want to display 0, at the time this A LED should be turned on, B LED should be turned on, C LED should be turned on, D should be turned on, E should be turned on, F should be turned on, G should not be turned on. If I want to display 2, then A, B, G, E, D should be turned on. If I want to display 9, A, B, C, D, F, G need to be turned on. E and G, E LED should be turned off. This is how you are going to display 9. If I want to display 3, A LED should be turned on, B LED should be turned on, G LED should be turned on, C as well as D should be turned on, F and E should not be turned on. Say suppose if I want to display the character that is A, at that time apart from D, each and every LED should be turned on. What if I want to display K? K I can't display like this because the LEDs are fixed position. So I have to display like this only. But if I am displaying like this, it resembles H. So LED displays, if I am placing like this, I can't display most of the characters, nothing but most of the alphabets I can't display. But all the numbers I can display using LED displays. So this is the drawback of LED display. But intensity point of view, LED displays are good and it is better. Nowadays in most of the houses, we are not going to make use of LCD display, we are going to make use of LED display in the case of television. This is the piece of Verilog code for LED display. So what they are given is module name they have taken it as 7-segment decoder. Outputs are seg, inputs are B, C, D as well as blank. So always at case B, C, D. When it is 0, 0, 0, 0, I am going to display 0. In order to display 0, I should not turn on G LED. All the LEDs I should be turned on. Similarly for 9, I have to turn off E LED. Rest of the LEDs should be turned on. So let us talk about multiplexers. So multiplexer is a combinational circuit. What it is going to do is, it is going to convert the parallel data to a serial data, or it is going to perform the serializing the parallel data. One more definition is, multiplexer is a combinational circuit which will be having 2 power n input and it will be having only one output. Which input should be driven to your output will be decided by your select line. The select lines are n select line. So let us talk about 4:1 multiplexer. So in the case of 4:1 multiplexer, you will be having 4 inputs. The select lines are 2 in number. So my inputs are I0, I1, I2 as well as I3. My select lines are A and B and output is, let me consider Y. So when A and B values are 0, 0, then I0 will be driven to your output Y. Nothing but multiplexer will be acting like a switch. If my inputs are 0, 1, then I1 will be driven to your output. If my inputs are 1, 0, then I2 will be driven to your output. If inputs are 1, 1, then I3 will be driven to your output. At a particular time, only one input will be driven to your output. This is very, very important. Multiplexers and demultiplexers will be used in communication. Next, let us talk about active low logic. So we'll be having 2 variants. The first one is active low logic and the second one is active high logic. So in the case of active low logic, we know that we will be having 2 variants in order to represent the data. The first one is logic low and the second one is logic high. So in the case of active low logic, what do you mean by 0? 0 means highest possible voltage, you are going to call it as logic 0, and lowest possible voltage you are going to call it as logic low. But in the case of active high logic, if I am writing 0, then it is the least possible voltage that the circuit can take, that one you are going to call it as logic 0. But if I am talking about logic 1, then it is highest possible voltage that a node can take. That one you are going to call it as active high, nothing but logic high. So this active low logic is called as negative logic, active high logic is called as positive logic. Usually we are going to consider active high logic only. Next, this is very important. NAND gate is also represented as bubbled OR gate. NOR gate is referred as bubbled AND gate. Verification of combinational circuits, how you are going to verify is with the help of truth table. With the help of truth table. The circuit which one you are going to test, that is called as device under test, that is DUT. Or which one you are going to verify, that is called as design under verification. Next, let us talk about sequential basics. So in the sequential basics you will be talking about sequential circuits. You should be in a position to distinguish the difference between combinational circuits and sequential circuits. The basic circuit element or the basic storage element is a flip-flop. We know that flip-flop is a bistable device which can store a single bit of information. That bit can be either logic 0 or logic 1. In the case of sequential circuits, your output is a function of present input as well as past outputs. This is very important. Now, this D flip-flop is also called as transparent flip-flop or transparent latch. Now, if my input is 0, my output is going to follow the previous state if clock is not there. If my input is 0, if I am applying clock, then output will be 0. If my input D equals to 1, if I am applying clock, then output Q is following D. Nothing but it is transparent. Whenever I am applying clock, whatever will be my input will be driven to your output. So it is called as transparent flip-flop or transparent latch. Next, you should know the difference between a latch and a flip-flop. We know that latch is level triggered, whereas flip-flop is edge triggered. And latches are used in buzzers. This is very important. One practical application of latch is buzzer. And flip-flops, we know that it can be used as a counter, it can be used as a register for storage element. Next, you need to talk about what do you mean by astable multivibrator, what do you mean by monostable multivibrator, what do you mean by bistable multivibrator. Nothing but you will not be having any stable state. In the case of monostable multivibrator, you will be having only one stable state, but in the case of bistable multivibrator, you will be having two stable states. Let us talk about counters. Counters are the sequential circuits which is going to perform either increment operation or decrement operation based on how you are going to apply the clock pulse. So if I am giving clock pulse to each and every flip-flop simultaneously, it is referred as synchronous counter. If you are giving clock to the first flip-flop, then for the second flip-flop, if you are deriving from the previous output, then that design is called as asynchronous design. You can able to realize the up counter and down counter using two techniques. The first one is synchronous technique and the second one is asynchronous. Next, let us talk about sequential data paths and control. In the case of sequential data path and control, you should talk about how your data is getting flowed from input to output, which path it is taking and which is the longest path. If you are having multiple paths, you will be encountering the race arrow condition. This is the drawback. If you are having multiple paths, then multiple delays will be there. Nothing but delay is not uniform. So in order to compensate with the delay, you need to make use of buffers or you need to overcome the race arrow condition. This is very important. Let us talk about finite state machine. You need to talk about Mealy model and you need to talk about Murray model. As you are very much familiar with respect to Mealy model and Murray model, in the case of Mealy model, your output is a function of your input as well as a state value. In the case of Murray model, your output is not a function of output, it is a function of only a state value. This is very important. So friends, in this video I have discussed combinational basics and sequential basics. In the next video, let us talk about memories. If you have followed with my lecture, please give it a big thumbs up. Also share this video with your friends and don't forget to subscribe to my channel, Precise Study. Thank you. All the best for your exams.